This is homework 4, part B, where we are going to find the flow rate of a 3-component system. So the system think of it as a tube where acetone and methanol are on the bottom of the tube with a screen that has air flowing over on top of it, and the screen is there for no like pressure vortexes or anything, but there is, it's not flow rate, it's rate of evaporation. But there is evaporation of methanol to air and acetone through air. So we know that the length of the tube is 0.24 meters long, and the pressure is constant pressure at 99.4 kilopascals. The temperature is maintained at 328.5 Kelvin. And now we are going to label these compounds as 1, 2, and then 3 for simplicity of writing the equations. So we know that, so y1, y2, and then y3. So we know that these are 0.319. These are millimeters cubed per second. And this is 0.528 millimeters squared per second. And then air is 0.153 millimeters squared per second. And then we know that the Maxwell diffusion coefficients are, for acetone, it's 8.48. We know that for methanol, it's 13.72, and then air, it's 20, diffusion coefficient is 19. 0.91. Sorry, these coefficients. Like that. All right, so then now we have to write the Maxwell equations for acetone and methanol. And it's redundant to do it for air because we know that y1 plus y2 plus y3 is equal to 1. So we're just going to do acetone and methanol. So let's write out the general Stefan-Maxwell equation for this. So this is the driving force of I is equal to the gradient of the mole fraction of I over position is equal to the mole fraction of I over the molar flux times the molar flux of J minus the mole fraction of J times the molar flux of I times the concentration times the diffusion coefficient of I to J. And we also know that concentration is equal to the pressure over RT. All right, so now let's write them for both acetone and methanol. So let's first start with acetone. So it's the driving force of acetone, and we labeled acetone as 1, is equal to the gradient of the mole fraction of acetone over position is then equal the mole fraction of acetone times the molar flux of methanol minus the mole fraction of methanol times the molar flux of acetone over times the concentration times the diffusion coefficient from acetone and methanol. And then we're going to add, oh, I forgot the summation. So now we're going to add, excuse me. So it's the mole fraction of acetone times the molar flux of air minus the mole fraction of air times the mole fraction of acetone times the concentration times the molar flux of, or the diffusion coefficient of acetone to air. All right, and then we're not going to do from acetone to acetone because that's redundant. It just equals 0 because going from the same compound, it just equals 0. So now let's go to methanol. So the driving force of methanol is equal to the gradient of the mole fraction of methanol over position. It's then equal the mole fraction of methanol times the molar flux of acetone minus the molar flux of acetone times the molar flux of methanol times the concentration times the diffusion coefficient of 1 to 2 plus the mole fraction of methanol times the net mole or the molar flux of air minus the molar flux of air times the molar flux of acetone times concentration times diffusion over concentration times diffusion coefficient of 2 to 3. All right, so now we have our Stefan-Maxwell equations. Now to make this easier for ourselves when we go to put it in Excel, we have to scale the positions. So this is the scale N, and this is the scale position from 0 to 1. So we would write this as N over the tube length over our actual position, or the position over the tube length. So then we take the derivative of the scale position over our actual position over the tube length. So then we can also write this as derivative of z position is equal to the tube length times the scaled position, and finally the tube length is equal to the position divided by the scaled derivative of the scaled position. So how we would do this for acetone would be the mole fraction of 1 over the scaled position equal to derivative of position over derivative the derivative of the mole fraction over the scaled position is equal to the derivative of the mole fraction of the position times the derivative of position over the scaled position. So then now we can implement this into the Maxwell-Stefan equation. So let's just bring this down really quick. So all right. So then all right. So these cancel out. So then that leaves us with the derivative of the mole fraction over the derivative of the scaled position is equal. And then we can also simplify this, like we said earlier, it's equal to the tube length. So we can write this as I'm just going to copy that. So that's for acetone. And we can also do the same for methanol. So methanol so it would be dy2 molar over, I need to plug this in real quick. Over the scale position equal to dy2 over the position times dz over dn. So then that leaves us with the derivative of the mole fraction of methanol over the derivative of the scaled position is equal to the tube length over this. Oh crap, this is not gonna fit. Okay. So now that we have our equations, we need to start with our initial guess when we put this in Excel for the molar flux of methanol. So we are going to take the Maxwell-Stefan equation for acetone, and we're just going to estimate. So we know that the gradient of the mole fraction of acetone over the scale position is going to be approximately equal to 1. So then we're going to expand this equation. So the molar flow rate of acetone, or the mole fraction of acetone times the molar flux of methanol. We're going to do the two blanks times the molar flux of methanol over concentration times the diffusion coefficient of 1 to 2 minus the mole fraction of methanol over times the tube length times the molar flow rate, or the mole, I've said it so many times. The molar flux of acetone over the concentration times the diffusion coefficient of acetone and methanol. All right, plus we're going to do the mole fraction of air times the tube length times the molar flux of acetone times the concentration of times the diffusion coefficient for 1 to 3. This is actually the mole fraction of methanol, and then plus the mole fraction of 3 times the tube length times the mole flux of 1 times over the concentration times diffusion coefficient of 1 to 3. All right, so we can go ahead and cancel this one out. This one equals to 0 because air going through air is 0. So now we can say that we know this one's approximately equal to 1. This is approximately equal to 1. Approximately equal to 1. Approximately equal to 1. All right. So now we are going to assume this one's not approximately equal to 1. We're going to take this part of the equation and calculate what the molar flux of methanol is for our solver, our initial guess. So we know that its concentration times the molar diffusion rate of 1 to 2 over position, and we know that the concentration is pressure over RT times the tube length. So now we're just gonna guess, and we know that pressure's it's on 99.4 kilopascals. We're gonna just round that up to 100, and we're gonna times that by 5 to get pascals. And then now we know that the diffusion coefficient from 1 to 2 is 8.48, and we're gonna just round that up to 10. We're gonna multiply that by 10 to the power of -5, and this is actually the power of 3 to get meters squared per second. And we know that R is 8.314. We're just gonna round that up to 10 joules per mole Kelvin. And then temperature, we're just gonna round that to 300. Ooh. And we know that the length of the tube is 0.24 meters. We're gonna just count that 0.02. So then that gives us 1/600 for our guess. And this would be the guess for the molar flux of acetone or methanol and acetone. All right, so now we're gonna move over to Excel. This is homework 4, part B. All right, this is homework 4B, part 2, where we are going to be calculating the rate of evaporation. And you're gonna see me look down to the right because I'm gonna be looking at my iPad. I can't get it on my screen for some reason, but just using my iPad for the equations, the Stefan-Maxwell equations. So first, let's calculate concentration, which is pressure divided by R times T. All right, and then dz, which is going to be equal to our length of a tube divided by 1,000. So those are each of the steps that we're going to be taking. And then the molar flow rate, or the molar flux of N1 and N2, we calculated that guess to be 1/600 divided by 600. All right. So now let's set up our table for our calculation. So it's a counter. Just 0. And then series, do columns and steps 1 to 1,000. All right, and then Z, which is equal to that, the counter times the length divided by 1,000. Let's go. And let's see if that went all the way to 0.24, and it did. Perfect. And now let's input y1, y2, which is these. Oh, no. Perfect. And now, no. Alright, and now let's calculate the Stefan Maxwell equation for acetone, which is dy1 over dr. That is our scaled position. So then that will be equal to the length, and this is gonna stay times and this is going to be multiplied by y1 times n2, and this is going to stay constant, and then this is minus y2 times n1 Alright, can I zoom in? No. Okay. Divided by the concentration times diffusion coefficient of 1 to 2 Alright, and then this is plus negative y3 times n1 divided by the concentration You know what? I should have made these formulas. If this doesn't work, then I'm going to make these formulas. The concentration of that times concentration gradient of 1 to 3. I can't put the, okay. Well. That looks about right. Okay. Okay, so now let's do it for acetone now, which is dy2 divided by dN. Alright, so it's basically the same equation, but instead of B6, it's that change times the concentration, B17. These are flipped. So it's the length of the pole times y2 times N1, which is minus H3, which should be H1 or G3 you know what? I don't like this. I need to turn these all into variables so it makes it easier for me to calculate it. So formulas. Right, perfect. Okay, so it's equal to D times Y1 times N2, no, yep, N2 minus Y2 times N1 divided by the concentration times D12. Alright, perfect. Now let's make sure that these perfect plus negative Y3 times N1 divided by C times D13. And then we need to make sure that this parenthesis, okay, and then we need another parenthesis all the way around this. Okay, so we actually need to make sure that these stay constant. Stay constant. Alright. And then no, it's the, okay, yeah, so it's, oh no. Okay. So copy this formula. So yeah, it's the same thing, but so instead of the first term being y1, it's y2. Okay. Times y1. So it's y2 times n1 minus y1 yeah, and then y1 minus, alright, and then yeah, so then it's 1, 2, perfect, and it's still times the concentration times diffusion coefficient of 1 to 2, and negative 3,1 times, and instead of that it's n2 is equal to that. So all right, perfect. Now we to find the concentrations, or to find the molar fractions of the rest of these, we use Euler's equation. So it's where you came from plus that times the step, and it's the same for y2, where you came from, plus the diffusion coefficient times the step, and then for air it's equal to 1 minus all of the others, acetone and acetone and methanol. Alright, and then now we can drag all these down. Oh, I forgot to make this stay. There we go. Okay. This one needs to stay also. right, perfect. All right, so now we are going to calculate so now we're going to calculate the sum squared. Oh shit. We need this is equal to FRG 1003. Yep. 1003, and then this is F 1003. Perfect. Now the sum square. Of these two. And we need this value to be as close to 0 as possible. So now we are going to use the solver for this. And we need to find the minimum of it, and we need to change these values to get that close to 0. What is happening? So yeah, we want B17 and 18, perfect. Solve. Okay. And now so the Maxwell-Stefan equation was a good yield for initial guess because this is very close, and 1 is very close to what we initially guessed, and if it wasn't close, then we wouldn't have been able to use the solver to be able to actually solve it. So it's a very good tool in chemical engineering to be able to guess the yield, so we can start to narrow it down to the actual percentage that we need it to be, so we're not guessing just random large numbers.